Alright, our goal today is to solve both exponential and logarithm equations, and so we are going to use some of the properties of logarithms that we've studied, but we're also going to just use some common sense properties. So I want you to take a look at these two statements. A lot of times we'll use these with exponential functions. I'm going to use this in example 1 and example 3. If we have the same base and those expressions are equal, then we can assume that their exponents would also have to be equal. Okay, and so if I said 2 to the x equals 2 to the 4th without taking any logarithms to bring the power down, we would be able to say, oh yes, if they have the same base and they are equal, x would have to equal 4. The same thing goes if you're comparing logs. As long as I have one logarithm of a same base of u, some expression u, is equal to log base b of v, I can assume then, if that is true, then u has to also equal v. We're going to use this first technique when solving example 1. So definitely we would like to isolate the base and then use a property of logarithms to bring a power down. But sometimes before we get to that point, we're going to be able to compare the expressions without having to take a log. Let me show you what I mean. First, as always, when we're solving an exponential function, we want to isolate the base, so I divide both sides by 3. So now I'm left with 4 to the x over 2 power equals 32. Now, absolutely, if we wanted to solve using logarithms, we could take the logarithm of both sides and bring this power down. But I notice that I could use this shortcut method from over here. I can write both 4 and 32 as a base of 2. And so how would I write 4? I would rewrite it as 2 squared. So I have 2 squared, because that's the same as 4, to the x over 2 power. And how could I write 32 as a power of 2? 32 is 2 to the 5th. So now I have the same bases. I'm going to simplify these exponents in a second. And so without taking a logarithm, I actually can simplify this. So if that were the case, the power to a power rule would state that I would multiply 2 times x over 2 together. That would give me 2. 2 times x over 2 is just x. So 2 to the x equals 2 to the 5th. What does x have to equal? X has to equal 5. In a moment, if we have time, I'll show you just a refresher of how we could, if we didn't notice that, use a logarithm to bring that power down. Let's take a look at this example. As long as we have one logarithm expression, what we can do is, first of all, number 1, if we just have one logarithm expression, our steps to do this kind of problem are we're going to isolate the log. And once we isolate the log, we've already done that, we're going to rewrite the log in its exponential form. So this is what I mean. This logarithm has a base of 4. So to rewrite an exponential form, I have 4. The exponent is on the other side of the equal sign, so 2 to the 1st equals 1 minus x. And below rewrite in exponential form, I'll just put a refresher from 3.3. We wrote that if you see this statement, this is its log form. To write it in exponential form, we do b to the y, the exponent is on the other side, equals x. And so that's all I did here. I did 4 to the first equals what's inside the logarithm expression. So this was b to the y. So if that helps you as you're solving these today. So 4 to the first is, of course, 4 equals 1 minus x. So I'm going to subtract 1 from both sides, and I get 3 equals negative x. And that would mean to find x, I would multiply or divide both sides by a negative 1. 3 divided by negative 1 is negative 3 equals x. Now going back, if I check in the original, because logarithms sometimes can have extraneous answers, if I would put this in, I'd get 1 minus a negative 3, which is 4. And sure enough, the log base 4 of 4, what power of 4 is 4? Is equal to 1. Okay. Third example. In this example, we're going to use a sum of our properties of logarithms where we rewrote using addition as multiplication and multiplication as an exponent. So back from 3.4, we learned that if I have the same bases, I can combine those logarithms that are separated by addition as the natural log of this times this. And I'm going to try to do that so I can simplify and get some kind of property like this. So I'm going to rewrite this as the natural log of 3x minus 2 times x minus 1. And on the right side of the equation, I'm going to go ahead and bring that power to the front. So I'm going to rewrite this as the natural log of x squared. Okay, so from above, I now have the log of something equals the log of something. If that is true, in order for these to be equal, is what is inside the natural log, those things have to be equal. So I'm going to go ahead and just make sure that what I've highlighted here has to equal what I highlight here. I'm essentially going to drop the logarithm out because really, as long as I'm taking the log or the natural log of both things, these highlighted expressions have to be equal. Now at the end, I do have to check for extraneous solutions. So what we have then is 3x minus 2 times x minus 1 equals x squared. So I multiply that out to give me 3x squared minus 3x minus 2x plus 2 equals x squared. I notice this is a quadratic, so I'm going to have to get a 0 on one side, so I can either use solving or quadratic formula. So I do that. I'm going to subtract x squared from both sides. And then I am left with 2x squared minus 5x plus 2 equals 0. As always, you can use factoring or quadratic formula. I'm going to go ahead and factor this because I prefer that method. So this is 2x and x. This is a minus and a minus, okay? And it has to be 2 and 1. This is going to be a 2 and a 1 in order to get negative 4x minus 1x. So I set each of those expressions equal to 0. So if 2x minus 1 equals 0, x would equal 1/2. And if x minus 2 equals 0, x would equal 2. Now because we dropped those logarithms out, we have to make sure that these work in the original because we can only take the logarithm of a positive number. And I notice a problem with this 1/2, and here's why. When I put 1/2 back in for x in either expression, I would get 3 times 1/2, which is 1.5. 1.5 minus 2 is a negative number. We can't take, that would be negative 0.5. We can't take the natural log of negative 0.5. Logs only exist when x is greater than 0. So if you can take a look at my graph a second, or not my graph, my calculator. If I put it in, 3 times 0.5 minus 2, it says non-real answer because it cannot calculate it. So we're going to go ahead and take this answer off. That is extraneous. However, 2 does work. 3 times 2 is 6. 6 minus 2 is 4. And 2 minus 1 is a positive as well. So x equals 2 is my only solution.